To talk about an alternative to fission called fusion. Remember, fission was where you fire a neutron into a nucleus of, for example, uranium-235, and the neutron causes the nucleus to split apart into two daughter nuclei, and with the release also of two neutrons. Okay, that's fission. Now, fusion is almost the opposite of that, and in fusion you take two small nucleuses and force them together, and if you force them close enough together, the strong nuclear force takes over and they join to become a bigger nucleus of a different material, obviously, with the release of a neutron and energy. Energy, again, being in the form of the kinetic energies of the neutron. Okay. An example of fusion would be if you take what's known as deuterium, H12, and add, or again, force that together with another nucleus of deuterium. And when you force the two together, if you can provide enough energy to force them together, you will then end up getting helium, which is two protons, and the helium will have not three neutrons, but the two protons and a neutron, and there is a release of a neutron. Now let's have a look at that. This has one proton, that's what identifies it as hydrogen, and it has one neutron. Okay, so the atomic mass is 2 and there's one proton. This is similar, so this also has a neutron and a proton, known as deuterium, D-E-U-T-E-R-I-U-M. When you fuse them together, you end up with two protons, so those two protons, one neutron, and an extra neutron that is released in capital N or small n. It really matters, suppose I should use small n. Okay? And a lot of energy is released as well. Okay? Now, that energy is released because the masses of the two individuals is actually less than the mass of the the combination of the two. But we'll talk about that later. Okay, another example of fusion is if instead of adding deuterium to deuterium, or forcing deuterium together with deuterium, if you force tritium, tritium again is an isotope of hydrogen. Both of them are isotopes of hydrogen, but tritium has two neutrons. And again, when you force the two together, you need to provide a lot of energy to do that. You will get helium, but this time you get the normal helium that we're used to looking at, helium-4 plus a neutron. So let's have a look. Combine these together. Okay, that'll give you your two protons, which identify now as helium. You've got a neutron and one of those neutrons, and the other neutron is the one that is released. Okay, and again, energy, high amounts of energy released when this happens, but it takes a large amount of energy to actually force them together, because they are, at the end of the day, nuclei that are positive, and you are trying to force together positive nuclei, two positive nuclei, and the electrostatic force is trying to push them apart. But if you can overcome and get them to actually close enough together that the strong nuclear force will take over, the strong nuclear force is stronger at that short distance, over that short distance, and it pulls them together, resulting in a new nucleus that is actually slightly less mass than the two nuclei that made it up, and the extra mass is released in the form of energy. Okay. Now, nuclear fusion is safer. If you look at it, nuclear fusion is safer than fission. Okay, basically there's less radioactive waste produced. You have no possibility of a runaway out of control situation. And the fuel is readily available. Deuterium is available. Remember, that's just an isotope of hydrogen. It's readily available in our oceans and it's easily and cheaply extracted. Okay? The only difficulty so far is huge amounts of heat energy are needed for that initial forcing of the two deuterium nuclei together. And so far they have not managed to make it so that the amount of energy that you put in versus the amount of energy you get out makes it a worthwhile exercise. But over the next 10, 15 years, that should be viable. And we now will have a far safer alternative to nuclear fission. Okay, very quickly then I want to talk about Einstein's mass energy equivalence. Okay, and then we'll go into the maths side of things. Okay, so basically mass is a form of energy. Einstein came up with this first of all theory, and then it was proven beyond doubt. So basically mass is a form of energy. So mass can be converted into energy and vice versa. Energy can turn into mass. Okay, and basically an example of that is if you take petrol and oxygen, you put them into a container and you burn them. There will be a reaction that will take place and energy will be released. This then is allowed to cool down, and if you measure the mass before versus the mass afterwards, there is a tiny change in mass, and that tiny change in mass is equivalent to the amount of energy that is released, that has been released. So the formula that equates mass to energy is E equals mc squared, the famous Einstein equation. The energy that you get from a certain mass is the mass times the speed of light squared. Now the speed of light is 3 × 10⁸ meters per second, which is a very large number. So for a very small change in mass, okay, you will get a large amount of energy out. Okay, so if you like, E equals delta m squared might be a better way of thinking about it. It's the change in mass, the amount of mass that is lost. That mass has basically been converted into energy, and the amount of energy that you get from a certain amount of mass is the mass times the speed of light squared. So you get a large amount of energy for a very small change in mass. For example, the nuclear bomb in Hiroshima, and you would all probably have seen the amount of energy that was released from that bomb. That was as a result of a change in mass of 1 gram. So 1 gram change in mass created that amount of energy, because the amount of energy that's released, if 1 gram of mass is converted into energy, the amount of energy that you get is the 1 gram, which is 0.001 kilogram, times 3 × 10⁸ squared is 9 × 10⁻16 joules. Okay, that's a huge amount of energy. Okay, yep, that's basically it. So the next few questions that we're going to be doing are mathematical, and they're using the formula E equals mc squared. Mass can be converted into energy, and that's the formula that you use.